A very warm welcome to everyone here. I'm Xavier, the chairperson of the Cambridge University Astronomical Society. Tonight, we are very honored to have Dr. Nigel Meredith with us to give a talk titled Celestial Incantations. Before we begin, please allow me to share a little more about our speaker. Dr. Nigel Meredith is a space weather research scientist at British Antarctic Survey. He uses satellite data to develop global models of plasma waves in near-Earth space for input into radiation belt codes and ultimately to forecast space weather. He is also interested in extreme space events and has recently applied extreme value analysis to long-term satellite datasets to determine the 1 in 10, 1 in 50, and 1 in 100-year space weather events. This is important for assessing the impact of extreme events on the world's satellite feed. He enjoys exploring how to make scientific data more accessible and is currently involved in an art science collaboration, Sounds of Space. He has published 128 papers in peer-reviewed journals covering a wide range of topics in space plasma physics. Now, without further ado, Dr. Nigel Meredith, please.
Thank you very much. Well, thank you for inviting me to talk to you this evening. As you've mentioned, my talk is entitled Celestial Incantations, and I'd like to thank my collaborators before beginning, and that is Kim Cuneo, who is a leading Australian composer and head of music at the Australian National University, and Diana Scarborough, who is a multimedia artist based here in Cambridge. Now, as a way of outline, I'm going to begin with an introduction on the sounds of space, focusing on Earth's natural radio emissions. And then I'm going to share a selection of the amazing sounds that we're able to receive using the Halley VLF Receiver in the Antarctic, before embarking on a sound-led, data-driven journey from Earth orbit to beyond the galaxy. I will then, about halfway through, start to talk a little bit about our art-science collaboration and how this has led to performances that fuse art and science, short films, and 2 albums. And I will finish by taking you through the tracks on our recent album, Celestial Incantations. And then hopefully at the end, we'll have time for some questions and answers. So our planet naturally produces a wide variety of radio emissions. And these radio waves are generated by 2 principal processes: lightning activity during thunderstorms, and also from geomagnetic storms, which are ultimately driven by the activity on the sun. Now, these radio transmissions are at the lower end of the radio spectrum, between 100 Hertz and 10 kilohertz. And they can be best detected by large antennae, either in space or on the ground. Now, the radio spectrum covers a broad range of frequencies below 300 gigahertz, and we use radio waves for a wide variety of applications, from radio astronomy and satellite communications at the highest frequencies, down through Wi-Fi, 4G, FM radio, AM radio, and for communications with submarines at the lowest frequencies, around 15 to 30 kilohertz or so. And at the lowest end of the radio spectrum, in a region where no man-made signals are assigned, we have the ELF VLF range, where we have Earth's natural radio. Now, the frequency range of the human ear extends over 3 orders of magnitude, ranging from 20 Hertz to 20 kilohertz. And this means that Earth's naturally occurring signals lie within this audio frequency range. Now, sound waves, as we know, are vibrations, typically of air molecules, but these emissions are a form of electromagnetic radiation, and so we cannot hear them directly. However, the recorded emissions can be converted to audio files directly and played back as sound, revealing a series of weird and wonderful noises. More generally, sound waves cannot travel in the near-perfect vacuum of space. However, electromagnetic and gravitational waves can both propagate in space, and taking these signals and converting them into sound is what enables us to hear the sounds of space. Now, the spectrum analyzer is a useful software tool that I'll be using during this talk to show you some of the signals. And it enables us to visualize the audio signals by plotting the amplitude or intensity of the sound on a frequency versus time graph. Just by way of introduction, because I'll talk about the magnetosphere a little bit in the first part of my talk, the Earth's magnetosphere is the region of near-Earth space which is controlled by the Earth's magnetic field. The solar wind coming from the sun compresses the sunward side to a distance of about 6 to 10 Earth radii from the center of the planet. But on the night side, the solar wind drags out the magnetosphere to a distance of greater than 1,000 Earth radii. Now, the magnetosphere supports a variety of populations of trapped particles. The plasmasphere, which occurs close to the planet, out to about 3 or 4 Earth radii typically, is a region of cold, dense plasma with energies typically of the order of 1 eV or so. The proton radiation belt is a region of trapped energetic protons, and the inner and outer radiation belts are regions of trapped energetic electrons with energies between about 0.1 and 10 MeV. And the inner radiation belt is relatively stable, and the outer radiation belt, which resides between about 3 Earth radii and 7 or 8 Earth radii from the center of the planet, is highly dynamic. Now, I'm going to start off the talk on Earth and share with you some of the sounds or some of the signals that we pick up with the Halley VLF receiver, which we see in this image here. Now, Halley Research Station, which is operated by the British Antarctic Survey, is a fantastic location to record Earth's natural radio, as it's magnetically connected to the outer radiation belt, where some of the radio waves are generated, and it's also electromagnetically quiet, being far from man-made sources. The Halley VLF receiver itself consists of 2 orthogonal 58-meter squared single loop antennae, designed specifically to detect the magnetic fluctuations of Earth's low-frequency radio waves. The weak signals which it picks up are amplified, processed electronically, and then subsequently digitized at 96 kilohertz. At BAS, we use the VLF-ELF data from Halley primarily to investigate the science of space weather storms, to help us understand potential space weather impacts on the Earth's climate system, and also for lightning detection as part of a worldwide lightning detection network. And as a remarkable spin-off, conversion to audio reveals a host of amazing sounds. Now, the main signals a ground-based VLF receiver will detect come from lightning activity, which is going on over the planet all of the time. Each lightning flash emits a short radio pulse known as a spheric, which covers a wide range of frequencies. And these are heard as short cracks and appear as vertical lines in a spectrogram, as we see on the right here. The spherics that we pick up from Halley typically come from the Amazon and Congo basins, which are both over 8,000 kilometers away. So let's take a listen to some spherics as recorded by the VLF receiver at Halley. Spherics can travel even further, up to halfway around the globe. The higher frequencies travel slightly faster than the lower frequencies, and these signals undergo an element of dispersion. The received signals are known as tweaks, and they have a pronounced ringing nature. Some of the radio waves associated with the lightning actually leave the atmosphere behind and they leak out into space. The signals can be guided by the Earth's magnetic field and received in the opposite hemisphere. They can even be reflected from the opposite hemisphere and detected in the same hemisphere as the original lightning strike. The higher frequencies typically travel faster than the lower frequencies, and the received signal has a characteristic descending tone known as a whistler. So let's take a listen to a whistler. Sorry, pure note whistlers travel along a single field line or closely spaced group of field lines, and they're heard as a clear whistling sound. Diffuse whistlers travel on multiple field lines which have different field lengths and sound swooshy in nature. Sometimes the whistlers bounce back and forth between the opposite hemispheres multiple times, and each successive received whistler becomes more dispersed as the signals travel further with each bounce. And this is known as a whistler train. Hopefully you're able to hear all of that. Sometimes the whistlers can excite additional radio waves, and these are known as triggered emissions. Another very prominent signal type, which we call chorus, is generated deep within the Earth's magnetosphere itself. Explosions on the sun cause bursts of charged particles and magnetic field that then subsequently travel out into space. When they reach the Earth, they can tear open the magnetic field, causing what is known as a geomagnetic storm. During such storms, energetic electrons are injected into the Earth's inner magnetosphere on the night side. They enter near midnight, drift around dawn to the day side, and are restricted to the region outside the cold, dense plasmasphere. The injection process leads to the formation of anisotropic electron distribution functions, which in turn excite plasma waves known as chorus. Chorus emissions are consequently enhanced during geomagnetic storms, and the waves are strongest on the dawn side of the planet from about 4 to 9 Earth radii, as can be seen from this statistical survey using data from 7 satellites. And in this figure, the sun is at the top and dawn is to the right, and 10 Earth radii is the outermost contour here. These waves are able to accelerate electrons to very high energies in the Earth's outer radiation belt. And studying these effects is important since these so-called killer electrons can damage satellites and also pose a risk to humans in space. And at BAS, we use global maps such as these in computer models to produce our space weather forecasts. The most common form of chorus consists of a multitude of rising tones in the frequency range from 1 to 5 kilohertz. And these emissions are known as chorus because they can often resemble the twittering of birds in the dawn chorus. Sometimes the signatures from chorus are more widely spaced and they can exhibit unusual complexity. This example shows some strong, rapidly rising tones. Plasmaspheric hiss is another important emission in the Earth's magnetosphere. And unlike chorus, plasmaspheric hiss is a broadband structureless signal and resembles audible hiss. Ray tracing studies show that a subset of chorus propagates from its source region in the outer magnetosphere into the plasmasphere with minimal attenuation. This subset is characterized by low relative frequencies and medium wave normal angles directed towards the Earth. And this source can account for most of the essential features of plasmaspheric hiss. Plasmaspheric hiss is also, therefore, enhanced during geomagnetic storms, and the waves are strongest on the day side of the planet from 2 to 4 Earth radii. And plasmaspheric hiss is largely responsible for the slot region between the inner and outer radiation belt. Now, I've been sharing individual signals with you so far, but different types of signals often appear together in the VLF recordings, and you can probably see a hint of this in the spectrogram at the top of the panel here. Now, this interval contains a medley of sounds comprising spherics, diffuse whistlers, rising chorus elements, and steady plasmaspheric hiss. So I'll play a section from this and see if you can recognize some of the sounds that I've been talking about. Okay, this is a second interval here where we have some strong, long-lasting chorus tones in the frequency range from 1 to 3 kilohertz. We also have spherics together with some diffuse and multiple whistlers and some relatively weak and constant plasmaspheric hiss in the background. Finally, I'd just like to share this one before we move away from the Earth. This interval contains some rising tone chorus, diffuse whistlers, and spherics. We also have some plasmaspheric hiss present below 2 kilohertz, with an intensity that subtly waxes and wanes over a period of about 4 seconds, and it produces an eerie background breathing sound. Okay, we're now going to leave the surface of the Earth behind and listen to some of these sounds that I've been playing, detected in situ in near-Earth space. So we're out now on the magnetic field lines that I showed earlier, out in near-Earth space. So whistlers which travel along these field lines can also be detected in situ by satellites. And this spectrogram shows a brief series of whistlers below 6 kilohertz. And these were detected by the Emphasis instrument on the Van Allen Probe ACE spacecraft back in 2015. you'll agree there's some fascinating sounds there. Now, sometimes the conditions in space lead to the generation of so-called nose whistlers. And these whistlers travel fastest at a particular frequency known as the nose frequency. So let's take a listen to some nose whistlers detected again by the emphasis instrument, this time on Van Allen Probe B in 2016. Chorus can also be detected in situ in space. This is where it's generated after all. And this spectrogram shows chorus emissions as a population of short, very intense rising tones between 0.5 and 1 kilohertz. And these emissions were recorded by the emphasis instrument on Van Allen Probe B back at the start of the mission in 2012. And you'll notice now that we're outside of the ionosphere, we're in the Earth's magnetosphere, there are no spherics in the background. This is like pure signal of chorus here, with the spherics which are only present, can only be detected near the surface of the Earth. They're now removed from the signals that we detect in situ in space. Chorus can also extend to higher frequencies. And this spectrogram shows some rising tone chorus in the frequency range from 1 to 2.5 kilohertz. And these emissions were recorded by the emphasis instrument on Van Allen Probe B in 2013. As on the ground, chorus that we detect in space can also exhibit unusual complexity. And in this example here, we have a pattern of rising and falling tones, which gives rise to S-shaped features in the spectrogram. Now, these emissions were recorded again by the emphasis instrument on Van Allen Probe B back in 2014. Now, natural radio is also produced on other planets in the solar system, most noticeably the gas giants, which also all have large magnetic fields associated with them. And chorus has been detected on each of Jupiter, Saturn, Uranus, and Neptune. Now, this spectrogram shows some signals recorded by Juno as it approached Jupiter back in June 2016. And these emissions were recorded at a distance of 128 Jovian radii, or 9 million kilometers from the planet. And this is the Jovian bow shock, where particles streaming from the sun first encounter the planet's magnetic field. So let's take a listen to Juno's arrival at Jupiter. Jupiter, interestingly, has lightning storms, which generate whistlers just like on Earth. And this spectrogram shows some whistlers at Jupiter recorded by Voyager 1 back in 1979. Chorus is also generated in Jupiter's radiation belts. And this spectrogram shows chorus at Jupiter recorded by Voyager 1 back in 1979. Now, Voyager 1 eventually crossed the heliopause and entered into interstellar space in August 2012. In this recording, time has been compressed so that 3 years plays back in about 18 seconds. And the events we hear are plasma oscillations in interstellar space, excited by solar activity. Now, all of the emissions I've played to you so far have been in the audio frequency range between 20 hertz and 20 kilohertz. But most electromagnetic emissions are not in this frequency range. However, they can be converted to audio by scaling the frequencies such that they fall into the audio range. And I'm going to share some examples with you now. Now, energetic electrons are emitted by solar flares. And these electrons produce radio waves at a characteristic frequency known as the electron plasma frequency. And the frequency of these emissions decreases rapidly with distance from the sun. Now, this spectrogram shows a type 3 radio burst produced by an intense solar flare back in 2003. And these observations were made by the Cassini spacecraft at a distance of 1.3 billion kilometers from the sun. Now, these emissions have been shifted downwards in frequency by a factor of 1,000, and the recording has also been compressed so that 4 hours is played back in 15 seconds. Rosetta detected magnetic fluctuations from comet 67P Churyumov-Gerasimenko. Now, these variations occurred at a rate of between 40 and 50 millihertz, which is well below the audio frequency range. And they were first detected when the Rosetta spacecraft was about 100 kilometers from the comet. And these emissions have been used to create a fully artistic piece by the German composer Manuel Senft. Now, Saturn is also a source of intense radio emissions. And this spectrogram was recorded by the Cassini spacecraft back in 2003. In order to hear this, the recordings have been shifted downwards in frequency by the Cassini scientists by a factor of 44. It has also been compressed so that 27 minutes is played back in 73 seconds. that has to be amongst my most favorite space sounds. We're now going to leave the solar system behind and take a listen to some sounds from the galaxy. Now, a pulsar is a highly magnetized neutron star with a mass greater than the sun, but a radius of only 10 to 15 kilometers. A tablespoon of neutron star would weigh around 900 billion kilograms, which is more than the weight of Mount Everest. Now, radiation is beamed out along the magnetic poles, and pulses of radiation are received if the beam crosses the Earth. And this is a recording of the brightest pulsar in the northern sky from the Lovell telescope at Jodrell Bank. The rotation period of this pulsar is 0.71 seconds. Different pulsars spin at different rates, and this is a recording of the Vela pulsar from the Parkes Radio Telescope in Australia. The rotation period of this pulsar is about 11 times a second. Some pulsars spin a lot faster. And this is a recording of the brightest so-called millisecond pulsar, also recorded by the Parkes Radio Telescope. And this pulsar is rotating about 174 times a second. Millisecond pulsars are thought to be old, rapidly rotating neutron stars, which have been spun up by attracting matter from a companion star in a close binary system. Sounds rather like an angry bee. We'll now leave the galaxy behind and just finish with a couple of extragalactic sounds. Now, gravitational waves were first predicted by Einstein back in 1916 and finally observed nearly 100 years later on the 14th of September 2015 by the LIGO interferometers in America. And this was the first ever detection of gravitational waves, which are ripples in space-time produced by violent cosmic events, such as colliding black holes and colliding neutron stars. And this chirp comes from the merger of two black holes that took place 1.3 billion years ago. About 3 times the mass of the sun was converted into gravitational waves in a fraction of a second here, with a peak power output of 50 times that of the whole visible universe. A couple of years later, on August 2017, LIGO made the first detection of gravitational waves from 2 colliding neutron stars that took place 130 million years ago. And this was the first ever cosmic event observed in both gravitational waves and light. The light-based observations showed that heavy elements such as platinum and gold were produced by the collision, solving the age-old question of where these elements are made. Coming back to Earth, this is a recording of air bubbles being released from an ice core collected from the Antarctic. And this particular sample is about 200,000 years old. And what we hear are the noises coming from the ice as the captured and highly compressed atmosphere of the past cracks and fizzes out. Okay, we now enter the second half of the talk, in which I'm going to talk about our art-science collaboration. Now, in 2017, we set up a multidisciplinary art-science collaboration to exploit these amazing natural sounds and hopefully to make them more accessible to wider audiences and also to have some fun at the same time. In 2018, we developed a show which we first performed at the Anglia Ruskin University as part of the Cambridge Science Festival. And this show included a science talk, followed by a performance with animations, soundscapes, music, and contemporary dance. following on from the success of this show, Kim Cuneo and his son Samurai traveled to the UK to be with us for a second show at BAS. And in this show, they performed live for the audience. So we had live music in the show for the first time, and that was really fun. In 2019, we showcased a new and immersive performance at Storey's Field Centre in Eddington as part of the Cambridge Festival of Ideas. And in this performance, the dancers moved amongst the audience as they responded to the sound-led, data-driven journey. And the dancers used this as a scratch night to test the reaction of the audience to their performance. In a separate venture, and basically at the same time, the Sounds of Space from Halley were incorporated into an update of the space simulation video game, Elite Dangerous. In this collaboration, I worked closely with Frontier Developments, the creators of Elite Dangerous, to incorporate the eerie sounds into the new gameplay. In any one of over 400 billion stellar systems, players can now use a new analysis mode to discover more about their surroundings. And the new mode, called the Full Spectrum System Scanner, features the simulated sounds of radio emissions from exoplanets in remote stellar systems based on the Halley VLF recordings. So let's just take a look at some sample footage from the game. So hopefully you were able to hear some of the Halley VLF sounds in that sample. In 2018, while Kim was visiting us at BAS, we started to work on an album combining sounds from the VLF receiver at Halley with original music. And for this project, we sat down together and chose a particularly active 24-hour period to set to music. Kim then went to work and matched a day of audio with piano music that he conceived of and played within another 24-hour period. The resulting album, Aurora Musicalis, was released in May 2020, and it's partly a soundscape drawn from our most mysterious continent and partly a response to the natural radio sounds of our planet. It invites us, the listener, to relax and enjoy the sounds of space set to ambient music on the grand piano. The album, which is available for free on Bandcamp, comprises 11 tracks, which enables us to experience the change of sound, the changing soundscapes at Halley throughout the day. It also contains a 3-minute compilation of the space sounds, both with and without music, and a music video featuring images from the BAS image collection. And I'll now share the music video with you with the 3-minute compilation of space sounds. Okay, I hope you enjoyed that music video. I'm now going to move on to Celestial Incantations and take you through our latest album, which brings the experience of space to all. And in this album, sounds from the Earth, the solar system, interstellar space and beyond are combined with music to take the listener on a journey from Earth to beyond the galaxy. Our journey begins on Earth, where we hear the sound of compressed air bubbles escaping from an ancient Antarctic ice core. The gases in the air bubbles are around 200,000 years old and provide a record of greenhouse gas concentrations long before detectable anthropogenic changes to the atmosphere. The sounds are combined with slow and solemn piano and surprising percussion of knitting needles on traditional bowls to symbolize the freedom of the gases. The track artwork evokes an ice core, a homage to melting fragments of ice, outwardly coherent, but internally complex. The second track, called The Earth and the Heavens Combine, features the natural radio sounds of our planet and also the acoustics of weather captured on 3 continents. We hear distant lightning and the clicks and pops of spherics and the pinging sound of tweaks. There are also the rising tones of chorus emissions, which I talked about earlier, and the descending tones of whistlers. The music is a piano work that has been reversed to give a disconcertingly unfamiliar effect. The track artwork is Earth and yet not Earth. Constellations, symbols, painted imagery combine with the globe to amplify both the known and the imaginary. We remain on Earth for the third track, which features the sounds of Whistler emissions recorded high above the Earth's atmosphere by the emphasis instrument on board NASA's Van Allen Probe A spacecraft. Have you heard a stone play before? Well, in this track, we hear a 110 kilogram polished granite stone bowed by hand while water is poured on it. The track artwork accentuates the crystalline using the contrast of dark sky against the cosmic abstraction to create a sense of white heat and energy. We travel to Mars for our next track, which features the first acoustic recording of the wind on Mars by the Mars Perseverance rover. In this track, we hear the Armenian duduk, possibly one of the most beautiful musical instruments in human existence. The doleful tones of the duduk and the newly composed lines sung by soprano Heather Lee are a reflection on the present state of the Earth's atmosphere, even while we celebrate the first terrestrial recording of the Martian atmosphere. The track artwork features the medieval symbol of Mars set over layered contemporary images of the planet itself. In the next track, we visit a frozen remnant of the formation of the solar system about 4.5 billion years ago. The sound of the comet is combined with a cellist piece by Chris Pidcock, which stretches the possibility of the cello in both pitch, harmonic language, and timbre. There's real drama in this work as the cello and the comet duel to take ascendancy. The track artwork is inspired by a Rosetta image of the comet evoking the spirit of an imagined soul split in two, emphasized with the glow and contrast to capture the journey of the lonely comet. We travel out further to Jupiter in the next track and encounter the Jovian bow shock. This track features no human instrument in voices. It's instead the Jovian wave sounds captured on board NASA's Juno spacecraft as it approached Jupiter for the first time in 2016 are compressed and processed into a 24-second reverb and delay loop. Other Jupiter sounds are processed with pattern enhancers, equalizers, and pitch enhancers to enable Jupiter to sing its own celestial song. The artwork for this track is a simple circle with the Veil Nebula, telling a story of power and energy as an abstraction from a traditional visualization of Jupiter. Our next stop is Saturn, where we experience the intense radio emissions I played to you earlier, recorded by the Cassini spacecraft. The sounds of string orchestra and Iranian Santor pulse with the composed imaginings of the rings of Saturn. The artwork uses an angelic or possibly demonic figure invoked with a manipulated image of a sea spider from the Bass archives, enveloped by a circle of stars. We leave the solar system behind to listen to recordings from Voyager 1 in interstellar space for the next track, Interstellar Incursions. The resulting sound is placed into a virtual Doppler to simulate the feeling of moving across space. Alongside, we hear the playful and accelerating sound of the North Indian tabla. The track artwork features a glimpse of the vastness of space through an imagined telescope portal. Our penultimate stop is the brightest pulsar in the night sky at a distance of 3,460 light years. The sound of the pulsar is combined with 900-year-old music composed by Hildegard of Bingen. The title of the featured song, The Symphony of the Harmony of Celestial Revelations, evokes the entire Sounds of Space project. The track artwork takes its iconography from the album cover design, recalling medieval influences, altered by a soft blue of ocean or sky in an emblematic talisman. We conclude our journey 1.3 billion light years from Earth, where we experience the chirp from the merger of two black holes. The music is performed in a virtual piano set up so that a switch triggers a note doubler. As the piece builds, we are set off on a roller coaster that is beyond human ability to play or even fully comprehend. The artwork features digitally painted, blended and distorted unrelated imagery. Patterns upon patterns converge in a kaleidoscopic abstraction to represent the almost invisible, yet infinitely complex. There we go. That's the end. I love the end in there, the duel between the piano and the black hole. Just finish with a slide here where we have some further information should anyone be interested. There's 2 articles in astronomy and geophysics, one called Turning the Sounds into Space, which I wrote back in 2019 about the beginnings of our collaboration, about the performances and the collaboration with Frontier Developments. And the second one is the one that's come out this month. It's the cover article, and it's entitled Music of the Spheres, all about our album Celestial Incantations. And of course, there are the links there to our 2 albums on Bandcamp. And that's it. I hope the sounds came over okay and that you all enjoyed the talk.
Thank you very much, Dr. Nigel Meredith, for the very interesting talk and the mesmerizing sounds. So now we will move on to the questions and answers session. If anyone would like to ask a question, please put it in the chat. Or if you prefer, you can also raise your hands and using the reactions button, and please wait to be called. We have a question from Kate in the chat. Where can we find the music?
So if I go back here, so if you go to Bandcamp and you search on Sounds of Space Project, you will find the 2 albums. The links are here. So if you can either type in everything, or you can just put Bandcamp into Google, and then Sounds of Space Project, and they should come up. And both albums are freely available for you to download or listen to. And if anyone wants a code, actually, Celestial Incantations is free, and it means that if you have the Bandcamp app on your phone, you can't kind of listen to it in the app. And sometimes that's nice to do. But we have some codes which we can give out because it's free. It doesn't go straight onto the Bandcamp app. But I can provide codes if anyone's interested, but you can still download it. That's just for the Bandcamp app. Whereas Aurora Musicalis, you can pay a small amount if you want to have it on the Bandcamp app. Otherwise, you can just download the sounds. And I also have a web page at BAS. If you just Google me and go to BAS, there's a web page at BAS where there's the story of our Sounds of Space project with various links in there, and you can even watch the show from the show that we did at the British Antarctic Survey was recorded live, and that's available on YouTube.
Maybe I will ask a question from myself. So what do you think will be the next step for this Sound of Space project?
That's a good question. I mean, I think it's always my dream to do this tour from Earth to beyond the galaxy. So it's been great to do that. We've got kind of 2 projects we're thinking about doing next, or in the process of working on. One is sonifying space weather data. So the data that we have and that we analyze for our space weather models and forecasts, we have various data streams that come in showing geomagnetic indices, for example, and maybe electron levels in the outer radiation belt and solar wind speeds, all these kind of phenomena that we're coming in and are basically time sequences, which Kim, as the musician, looks at them and he thinks, oh, that's fascinating, I can convert that into sound. So he's kind of working on that at the moment, and we're looking forward to seeing what comes out of that. We're also thinking of looking a bit more closely at the sound of the sun as well in various forms. So yeah, we're hoping. At the moment, we've kind of gone back to the drawing board. You know, it takes a while, as you can imagine, for these albums to kind of be born, and it starts off as a fun process between the 3 of us. We just all get together and we try different things, and the album Celestial Incantations basically came about initially through the performance, because we had the music in with the performances and the soundscapes, and so it gradually grew from there over time. And it was fantastic when we eventually had enough material for an album. And so now we're at the stage of we're going back to the drawing board and working with new music and new potential sources. So it's all very exciting, and we don't quite know exactly where it's going to go yet, but that's part of the fun.
Right, thank you for the answer. So maybe just another question. So for the most part, this project has been a conversion of time-based signals into sounds. Has there been any thoughts about converting sort of spatial signals, like maybe spectrums of the sun or spectrums of other objects into sounds?
No, we haven't looked at that yet. I've seen some interesting examples where astronomers have done this with images of galaxies and nebula and things. And it is rather fascinating what they produce. When we look next to work with the sun, there won't be so much in the way of kind of recordings that we can use. There's the type 3 solar radio burst that I shared with you earlier, and there's also sounds of the sun that you can get from vibrations and things on the surface of the sun. But we may need to be kind of more adventurous in the way that we interpret what we get if we want to use images of the sun. For example, the EUV images and things, they're absolutely beautiful, and then having the coronal holes and coronal mass ejections and things. So looking at using them in our art and music will be an interesting challenge.
Right. So we have a question from Amy in the chat. So she asked that she is very much a layman, and she would like to find out if so her fiance has spent time at Halley and is currently at Rothera, and she's just wondering if there are any recording devices there that that's recording similar sounds, and if not, if there's any particular reason for that.
Yes, there is. One of the scientists in our group, Mark Gilbert, he operates the VLF antennae, and he operates the obviously the VLF receiver I showed here at Halley, but he also operates other smaller receivers at various locations around the world. I think there's one in Rothera, and they're part of a network. They're part of a worldwide lightning detection network, but they also rather cleverly monitor signals from VLF transmitters. Now, VLF transmitters generate high intensity radio waves for basically used by the military to communicate with submarines, but these VLF receivers can pick them up. And by looking at the amplitude and phase of the signal, they can work out information about electrons precipitating from the radiation belts and coming and the effect they have on the ionosphere. So there's a lot of interesting work that the group do and scientists do around the globe using information from this so-called aardvark network of VLF receivers, and there's definitely one at Rothera.
All right, thank you. And also, second part of the question asks, what do you think is the most important thing we can learn from these sounds in relation to the future of our planet?
I think that's a really good question. I think the emissions that we detect in space are the ones that we detect on the ground as well, obviously, but they can have a profound influence on the electrons in the Earth's radiation belt. So we use those signals to help us forecast space weather, which is really important for the satellite industry. The number of satellites in near Earth space is growing all the time, and being able to provide forecasts to satellite operators and engineers is very important, and it's only going to get more important with time. And I think that's the perhaps the largest, the most important area in which the kind of VLF wave research, if you like, will contribute to our kind of knowledge and applications, at least in the over the next decades or so.
All right. If there are no more questions, that will be all for tonight. Thank you everyone for coming, and I hope you've enjoyed the talk. Thank you again to Dr. Nigel Meredith for the wonderful talk. Good night, everyone, and we hope to see you again for the next week's talk.
Bye now.
Thank you.